Hello guys, so this is lecture 3.3, and this is a long one. So this one is about Bernoulli numbers. So okay, so let me maybe say a few words about Bernoulli numbers even before we start. So Bernoulli numbers is a sequence of numbers b0, b1, b2, and so on. b0 is equal to 1, b1 is 1/2, b2 is minus 1/2, b2 is 1/6, b3 is 0, b4 is minus 1/30, and so on. b6 is 0, b5 is 0, and so on. Sorry, that's b4. b5 is 0, and so on. So, okay, so this sequence appears in many questions in mathematics, in various asymptotics, in various explicit formulas, in various combinatorial problems over and over again. And in particular, it appears in this problem about summing powers, which we already came across. And of course, it's a very good question why that happens. So I want today to not only explain exact formula for the sum of powers, which we will do, but also to explain a pretty conceptual reason where Bernoulli numbers come from there. And this is related to something called calculus of operators, and in general operators on polynomials and power series applied to operators. And this is an interesting and deep circle of ideas. Okay, so let me maybe just before even doing anything serious, let me just maybe give a definition so that you will at least know what Bernoulli's numbers are. And definition is as follows. So consider a function. So power series e power x minus 1 over x. One can easily write down what it is. It is 1 plus x over 2 factorial plus and so on. It starts with 1. And as you remember, everything which starts with non-zero constant is invertible. So power series is invertible. So, and then we can write down inverse, x over e power x minus 1. And then I can write it down as a power series. And what I will do, I will write it down in the following way. b0 plus b1 x over 1 factorial plus b2 x squared over 2 factorial plus and so on. So you see, so these things are called, so these are Bernoulli numbers. So basically, the idea is that you take a beautiful power series with this explicit formula and just its coefficients times factorials are called Bernoulli numbers. Of course, you can ask why I decided to write it down in this. So usually, let me put it this way. So usually people will say that ex over ex minus 1 is, this is just a notation, is exponential generating function of Bernoulli number sequence. So it means that you take the sequence and then write down a function every time taking x over 1 factorial, 2 factorial, and so on. So x power n over n factorial. Okay, so this is a definition, and one can easily compute the first few terms, and even one can write down some formula for them. I mean, you can always just, you know, if you just let's prove something about Bernoulli numbers. So if you just take this and multiply on e power x minus 1, so you know that e power x minus 1 times x over e power x minus 1 equals to x. And then you can just, you know, write it down. So so it means that if you take this b0 plus b1x over 1 factorial plus b2 over 2 factorial x squared plus and so on, and multiply it on e power x minus 1 over x. So 1 plus x over 2 factorial plus x squared over 3 factorial, you know that you will get 1. And so if you just write it down as identities, you can say that, okay, b0 equals to 1, and then with power x we'll have b1 over 1 factorial plus b0 over 2 factorial is equal to 0. Then b2 over 2 factorial plus b1 over 1 factorial 1 over 2 factorial plus b0 over 3 factorial equals to 0, and so on. And of course, it is easy to rewrite. So in general, you can say that. Let's see. So probably the easiest way is to multiply on 3 on n factorial. So in general, we will have okay, so I just want to generalize it. So I will say that n plus 1 bn plus n plus 1. So this is n plus 1 choose 1, n plus 1 choose 2, bn minus 1 plus n plus 1 choose 3, n plus 1 choose 3, bn minus 2 plus and so on. And so I multiplied on so my goal was to multiply on n plus 1 factorial, so up to n plus 1 choose n plus 1 b0 equals to 0, and this gives me immediately recurrence relation. So so this is a way to compute them on your computer or something like that. So if you know all numbers before bn, you can compute bn. Okay. Moreover, let's see. So some properties of these numbers are quite straightforward. So for instance, there is this property that odd numbers are equal to 0 except b1. So let's see where this comes from. So that's not very hard. So claim is that b 2k plus 1 equals to 0 for k okay, for everything except b1, so for k bigger or equals than 1. So proof is as follows. So proof, for this, let's take our function. So we know that x, let's see. Yeah, so we know that x over e power x minus 1 is equal to b0 plus b1 over 1 factorial x plus and so on. And then we can just plug in minus x. So minus x over e power minus x minus 1 is, as we discussed, we just, you know, when you substitute something in a power series, so you will get just b0 minus b1 over 1 factorial x plus t, and you will have eventually minus 1. So minus 1 bn x power n over n factorial, and so on, minus 1 power n. And so then we can just add them. So x over e power minus x minus 1. Oh, sorry. So I want to show that odd guys vanish, and the odd guys are those which change sign here. So let me subtract. Let me take x divided by e power x minus 1 minus x over e minus x minus 1. So then I can easily compute what this gives me, and this is just x minus plus x e power x Yeah, sorry. Yeah, so this gives me x plus x times e power x, x minus x times e power x divided by e power x minus 1, which equals to minus x. And so what it means, so I took my, and on the other hand, so what I did, on the other hand, this equals to, so I had this sum, so this was sum bn x power n over n factorial, and then I subtract, and this is where I substitute sign before x, bn minus 1 power n x power n over n factorial. And of course, when I do that, so terms with even degree will kill each other, and so I will get sum b 2k plus 1 x power 2k plus 1 over 2k plus 1 factorial for k starting with 0, but this is minus x, and and each time I will see it twice. And so what it means that b2k plus 1 equals to 0 for k greater or equals than 1, and b1 times 2 equals to minus 1. So b1 equals to minus 1/2. So you see that this function is not exactly odd, not exactly even, but very close to be even. If you shift it a little bit, you will get an even function. So that's why every odd Bernoulli number vanishes. And this is, by the way, how you can prove something like that using generating functions. So vanishing of odd numbers or vanishing of even terms of sequence is actually related to a function being even or odd. Okay, so far I said nothing very interesting. We just took some pretty random generating function and called its coefficients Bernoulli numbers, and of course we start immediately deriving properties, recurrence formulas, and other stuff. So now I want to explain what Bernoulli numbers have to do with the problem which we were talking about, the sum of powers, and why. Okay, so let me formulate a main theorem, and it will make no sense at all. So, main theorem for today's lecture, and then we will see how to apply it. So, theorem is as follows. So, I will explain everything later, but the idea is that there exists an operator, integral from x to x plus 1. So this will be something which takes polynomials to polynomials, and this is some operation of polynomials. You can guess which. Has an inverse. And this is the one which, if you do this one backwards, you will get it. And the answer is that this equals to d divided by e power d minus 1, which is b0 plus b1 d over 1 factorial plus b2 d squared over 2 factorial plus and so on. So whatever the statement means, this is the fundamental reason why Bernoulli numbers appear at all in various questions, and they relate basically an operation of integration, its inverse, and d over 1 factorial, d2 over 2 factorial, and so on are kind of you can think of it as sort of taking coefficients operators. So let me try to explain what I wrote here, and for this I need a pretty serious side story to explain to you, pretty serious side story about operators. So operators on polynomials for concreteness. So, okay, so consider a vector space of polynomials. So vector space of polynomials is, this polynomials with rational coefficients for simplicity, and then we can add them, and then we can multiply them on a scalar, where lambda is some rational number. And we basically think about these two operations as what we do with polynomials, then we talk about a vector space. So, so the fundamental definition here is what is an operator. So an operator, also called a linear map in linear algebra, operator is a map, say L, from this Q of x to Q of x. So something taking polynomials to polynomials such that L of P plus Q equals L of P plus L of Q, sending sum to sum, and sending this multiplication on scalar to multiplication on scalar. So in linear algebra, these guys are called linear maps, and linear algebra studies them in all detail. So they are related to matrices and so on. We are not going to talk about it. Also, our vector space is infinite dimensional, so one should be slightly careful here. Okay, what examples do we have? So examples are, the main example is probably derivative d, taking a polynomial p to p prime. And another example is, for instance, this delta. And delta sends p to p of x plus 1 minus p of x. And the third example is this one, integral x plus 1 applied to p is by definition, this is just, integral. So whatever, this thing. So for instance, if you take, let me do an example. Let's take x squared minus 2x. So if I apply d to x, d of this p is equal to 2x minus 2. Perfect, that's usual derivative. So delta of p is equal to, let's see, so x plus 1 squared minus 2x minus 2 minus x squared minus 2x, which equals to minus 2x minus 1. That's weird. No, that's fine. Okay, this is delta p. What about this one? So integral from x to x plus 1 of our p is, of course, s plus 1 cube over 3 minus x cube over 3. So this we applied our operator to x squared minus 2 x squared over 2 x plus 1 squared over 2 minus x squared over 2. Let me not even compute it. Or actually I can. Let's see. So this is x squared plus x plus 1/3 minus x plus 1 squared is 2x is x plus 1/2 minus 2x minus 1, which is x squared minus x minus 2/3. Okay, so various, operators. Notice that this one and this one decrease the degree. So we know when we differentiate or takes a difference operator, degree becomes smaller. And this one does not, so this one preserves the degree. And this will be very important because the fact that it preserves the degree is actually in charge of the fact that there exists an inverse map. The inverse map is just, the one which you want to apply to polynomials, so that if you take that and apply this guy, you will get your polynomial back. Okay, so what one can do with operators? So one can do with operators some sort of algebra. So let me say it here. So operators form a ring, and there are two operations. So one can, if you have L1, L2, you can just add them. And of course you can compose them. You can just take one and then another. And so this we think of multiplication, and this is addition. And they satisfy usual properties of addition and multiplication. So let's have a look at something like that. For instance, I can take example. I can take, for instance, an operator which will be delta minus d. That's a typical operator. let me call it L. And then I can apply L to P of X, and this will be something like P of X plus 1 minus P of X minus P prime of X. So why the story is interesting is that actually there are some interesting identities between operators, which are non-trivial and which are kind of important, and it is much more simple to first understand fundamental properties of these operators and then to actually start, proving some identities or looking at some concrete problems like sum of powers, because it might happen that fundamental relations between these operators are in charge of all the magic we have seen. So let me give you another example. For instance, one can take, D applied to integral from x to x plus 1. And the claim is that this is equal to delta. So why? Because, if you take some polynomial p, then of course when you take the derivative of integral from x to x plus 1 p of t dt, by Newton-Leibniz formula, which is of course true here, derivative is equal to p of x plus 1 minus p of x. So if you wish, this one decreases degree by 1, this one decreases degree by 1, and this one preserves the degree. So in linear algebra you would say that basically this times this is this. So if you know that this one has an inverse, it allows you to go between d and delta and backwards. So but this is just an example of some multiplication property in this interesting ring of different operators. Okay. So now, let me ask the following thing. What is the relation between delta and d? So, what is the relation between delta and d? Can one write one of them in terms of another? And there is some hope probably, because we know that roughly speaking, derivative is, so difference is you take p of x plus 1 minus p of x divided by x plus 1 minus x, which is 1, and this is very close to derivative, so probably they are not that much different, and the question is, what is precise relation between them? So I will say what is a precise relation, and for this I need one interesting idea. So, we can multiply operators, we can add them, but there is another thing we can do which is maybe much more surprising. So this delta and d have the following property. So let me give a definition. So little definition. So operator L is nilpotent if for every polynomial p of x there exists a big degree n such that L power n applied to p vanishes. So it means that if you take some operator and apply it over and over and over and over to some polynomial, you can always get to 0. So that's a definition, and of course we have a lot of such nilpotent operations. D and delta are examples of those, because every time you apply them, degree goes down by 1, and so if you apply d more than degree times or delta more than degree times, you will get 0. So they are nilpotent operators. So why nilpotent operators are interesting? For the following fundamental reason. You can plug them in power series and get new operators. So that's a deep and strange idea. So deep and strange idea is that, a priori, if you have a power series, it has infinitely many terms. And what it means to plug in d. So what is this one, for instance? I wrote it down before. What is this sum, right? But the answer is it's actually very meaningful, because imagine you have this infinite sequence. Of course, it looks like crazy operation, and but in fact everything is fine, because if you apply it to a polynomial of degree n, only first n terms will give you something, everything else will be 0. So you can define this expression applied to a polynomial just looking at the meaningful terms. It will be 0 starting with some term. So this is why one can actually apply plug in operators in power series if operators are nilpotent and get new operators, which are, operators from this definition's perspective. And let me maybe first formulate it precisely, and then I will explain this theorem. Okay, so definition. So this one is a bit. One should be very careful here. So let's suppose that we have some f of x, a power series, with rational coefficients. Everything is rational here. So this f of x is, as usual, it has some, coefficients like this. And then let's suppose that L is some nilpotent operator. And then the idea is then Fl applied to P equals to A0 times P plus A1L applied to P plus A2L squared applied to P. This is L of P, plus and so on. And this expression always equals to 0 somewhere, because at some moment, L power something applied to P is 0. So this is the definition, and it has all the usual properties you expect. For instance, if you take product of power series, plug in L, you will get so f times g of L equals f of L times g of L, and so on. All the usual properties apply, just because it is really easy to see that powers well commute with each other, and so that's pretty straightforward. One can do that. So there is this interesting notion, plugging in operators which are nilpotent into power series. Here is a somewhat interesting example. Let's, for instance, take 1 over 1 minus d. So that's an operator, and by my definition, one can think of it as like 1 plus d squared plus and so on. Perfect. So on the other hand, so this should be, so one can also think of it in the following way. So there is an operator P goes to P minus P prime, and this one is an inverse. So this one is returning back. Let's see. Yeah. So this is what my operator does, and I can compute it. For instance, if I want to apply it to some concrete polynomial, just let's take something like, I know, like x. Let's take x cubed minus x, just for instance, or x squared minus x. Don't want to compute too much. So when I apply 1, I get x squared minus x plus the derivative plus 2x minus 1 plus the second derivative plus 2, which is just x squared plus x plus 1. I mean, you see, that's totally meaningful thing one can do. To every polynomial, you can take polynomial, first derivative, second derivative, and so on, add them up, get a new polynomial. And though this expression, formally speaking, has infinitely many terms, everything after degree 2 will give you 0 when you apply to degree 2 polynomial. Okay, so theorem. Delta equals e power d minus 1. So that's the relation between difference operator and differentiation operator. So what this means, again, it means I take a power series for e power d, subtract 1, and plug in d, and this is just d plus d squared over 2 factorial plus and so on. So let me prove it. The proof is immediate. This is just Taylor's formula. So Taylor's formula. I mean, by Taylor's formula, I remind you from last time that we have p of x plus y equals to p of x plus p prime of x over 1 factorial y plus p double prime of x over 2 factorial y squared plus and so on. And I can plug in y equal to 1 and move p of x here, and then I will get the delta p of x, which is p of x plus 1 minus p of x, equals to d over 1 factorial p plus d squared over 2 factorial p plus and so on. So this is what I see here, and I plug in y equal to 1. And then, of course, that just, since it's true for every polynomial, it means that delta equals d over 1 factorial plus d squared over 2 factorial plus and so on equals to, by definition, e power d minus 1. So we have this beautiful relation. And, okay, wonderful. So I want, for solving this problem about sum of powers, I want to find what is the inverse of my delta operation. But delta as an operator clearly doesn't have an inverse, just because, I mean, it lowers the degree and sends constants to 0. And so inverse operator, if it existed, would have to do something with 0 to get back your constant, but, you know, it doesn't know which constant to take. So it doesn't have inverse. But something very close is true. So let's see. So let me take my okay, so claim. So theorem 1, theorem 2. So operator p goes to integral from x to x plus 1 p of t dt is invertible. And integral from x to x plus 1 inverse is equal to t to d divided by e power d minus 1, which is, formally speaking, b0 plus b1 d over 1 factorial plus b2 d squared over 2 factorial plus and so on. So this is the statement. Okay, so to even make sense of it, we need to be very careful. So what do I mean here, and why this is true? So let's see. So claim. So let me prove it. So proof. I mean, the fact that yes, okay. So proof is as follows. So step 1 is that integral x plus 1 equals e power d minus 1 over d. So this is again something which is really easy to write down. So this is let's see. So this is 1 plus d over 2 factorial plus d cubed over 3 factorial plus and so on. And so the statement is that if you apply it, if you take an integral of any polynomial and take this thing of any polynomial, that's the same thing. And proof is just, you know, this is just binomial formula. So if you take as a polynomial x power n, then on this hand side you will get x plus 1 power n plus 1 over n plus 1 minus x power n over x power n plus 1 over n plus 1. And when you apply the right hand side, you will get what you get if you expand it using binomial formula. You will get x power n plus n over 2 factorial x power n minus 1 plus n, 1 second. Yeah, plus n times n minus 1 x power n minus 2 over 3 factorial plus and so on. And if you multiply by n plus 1 and add by n plus 1 and move x n plus 1 to the other side, you will get binomial formula. Since the statement is true when you plug in any monomial x power n, it is true for every polynomial because it's linear operators and each side is linear, and so to check it for a polynomial it's enough to check for each monomial. So that's one proof. Another proof is you can kind of apply derivative to it and see that you get this identity actually. So then you can check that it is true for constants, and this implies the statement. So one can prove it in various different ways, but that's not very surprising. So after all, this is, yeah, you see, like almost binomial formula. But then we know that this operator has an inverse. Why? Because this power series has an inverse. It starts with 1. And if you have some power series, if you know that when you take this power series and multiply by this power series, you get 1 for power series, when you plug in inside D, of course, you still get 1, just because this plug-in commutes with multiplication. And it means that the inverse of this operator is actually given by this function, and so we get the statement. So maybe let me reformulate it in a more down to earth terms so that it will be less confusion what I actually mean. Okay, so again, let me just reformulate it. So what it means, it is equivalent to the following. So suppose you have two polynomials, and suppose you know that p equals integral from x to x plus 1 q. I mean, this is p is this operator applied to q, but this is just equality of two functions. This is just integral as usual integral. Everything is depending on x, and this is t dt. And the claim is that then you can take the inverse, and what it means, q of t, q of x equals 2, and then you need to take this thing and apply it to p of x. B0 plus B1 P factorial, P prime over 2 factorial plus B2 P2 prime over 3 factorial, B0, B1 over 1 factorial plus P2 double prime over 2 factorial plus B3 P3 prime over 3 factorial plus and so on. And again, this vanishes when we take more derivatives than the degree of p. So this is very interesting because in analysis, I mean, you know that kind of differentiation and integration are inverse operations. But apparently, if you apply them just to polynomials, you can say something very precise. So if you know that p is an integral of q, you can compute q completely explicitly. I mean, this integral should be from x to x plus 1, and then you have a formula with Bernoulli numbers, sorry. So this is why Bernoulli numbers appear over and over, because they sort of give you inverse of integration from x to x plus 1 operation. Of course, you can ask me what happens if p and q are just continuous functions, and then the answer is that it is not exact equality, but you can get a lot of heuristics trying to sort of play with it, because when your continuous function is actually polynomial, it will be true, and in other cases there might be different correcting terms. Okay, so now let me apply all the story to sums of powers. So recall that we were trying to understand the following. So we had this power 1 power k plus 2 power k plus and so on, and these days I will stop at n minus 1 power k, and this is some polynomial let me call it sk of n. And what we have already seen that, so this sk of n is a polynomial. And we proved that it is a polynomial. Even we even checked last time that sk of 0 is equal to 0. So there was this statement that if you have arbitrary polynomials, then you can solve this equation delta equal to this polynomial with additional condition sk of 0 equal to 0, and this is of course what we got. So the question is to compute it explicitly. So sk is a question mark. So let me apply all the story. So what I know about sk, so I know that delta applied to sk of x is equal to, and then it will be n power k. Sorry, x power k. Okay, and I know that so delta, so this can be rewritten as let's see. So this can be rewritten as e power d minus 1 applied to sk is equal to x power k. Perfect. So I don't know how to take inverse of e power d minus 1. This is what I would love to do. But let me rewrite it instead as e power d minus 1 divided by d applied to d sk. And this is, of course, again, x power k. So I can do that because this is just, I mean, after all, I had this 1 power series multiplied by d, applied it to sk, that's absolutely legitimate. And now the only thing which I need to keep in mind is that this one is now invertible. So dsk equals to, and then I can take the inverse applied to xk. So this one, b0 plus b1 d over 1 factorial plus d applied to x power k. And this is amazing because I have basically computed the derivative of my polynomial. I know that at 0 it equals to 0. That allows me to compute my polynomial completely. And this is something I can easily write down. So let me finish now. So this implies that dsk equals to b0 plus b1. Derivative of xk is k x power k minus 1 over 1 factorial plus b2 k minus 1 over 2 factorial xk minus 2 plus and so on. And so this is, of course, these are just binomial coefficients, and eventually it will go up to b k times, so k minus 1 over 2. So here I see binomial coefficients, and it will end with 1. So here I will see k choose k. And so then I can take the, so this is a derivative, and of course the inverse operation will be integration, simply because I know that my polynomial at 0 equal to 0, so it doesn't have any constant term, and so then I get that sk of x equals, okay, so, sorry, b0 x power k. So b0, which is 1, actually, x power k plus 1 over k plus 1 plus b1. Then, okay, so I have here k choose 1 divided, so k choose 1 times integral of x power k minus 1, x power k divided by k plus b2 k choose k minus 1 x power k, sorry, k choose 1, k choose 2, I'm sorry, x power k minus 1 over k minus 1, plus and so on, up to bk x. So this is the formula, that's the end. So you see, basically the main idea here was that so relation between sk and simple powers is just this delta. Delta sk is x power k. So delta takes sk to something very simple. And so we want, of course, to take delta inverse, except one cannot do it. So instead of taking delta inverse, we took delta, we applied the derivative here, and then we took inverse of d divided by e power d minus 1, which one can do. And this uses Bernoulli numbers. So that's the total formula. Let me maybe formulate it in a slightly different way. So there is a following mnemonic formula. So sk of n is equal to b plus x power k plus 1 minus b power k plus 1 divided by k plus 1. And that doesn't make any sense. So what you do here is you write down your binomial formula for b plus x power k plus 1. Instead of every power of b, you just take the corresponding Bernoulli number. So you will see x power k plus 1, everything divided by k plus 1, plus k plus 1, and here I see b0, b1 x power k, and here is b1 x power k, plus k plus 1 choose 2, b2 xk minus 2, plus and so on, and it ends it ends at power of x, and I get bk times k plus 1. So that's the mnemonic formula. There is an area of math called shadow calculus, which explains what that means. I'm not going to talk about it at all. A few messages to take from here. So first, one can and should study not only vector spaces, polynomials, and so on, but operators on them, operations with them, like derivative, delta, integration, and all relations between them. So second message to take home is that there is a beautiful relation between d and delta using exponent, and that one can actually take exponents, power series applied to nilpotent operators, and this is the only way to actually explain the precise relation between many operators. So third is that there is this power series with Bernoulli numbers coefficients, which is easy to find, and fourth is that it's exactly inverse to the integration operator. I didn't use precisely the statement in the proof, but it's hidden here, you can reformulate it using it. And then if I want to solve my powers problem, what I need to do essentially, I need to invert my difference operator, and I cannot exactly do that, but with a trick I can if I take delta divide by d and multiply it by d, I can instead invert this thing and then integrate and get my answer. And eventually there is a beautiful formula with Bernoulli numbers. So I know that was maybe a little bit hard and maybe a little bit abstract, but so I hope you start to appreciate power series more and more, because the fact that they are not actual functions, you don't worry about convergence and so on, means in particular that you can plug in anything, you don't need to care. So for instance, you can plug in such thing as a symbol for derivative, or symbol for delta, or symbol for integration, and this all makes sense, because this one does not, and delta and d do make sense. For instance, you can even start doing something weird. You can start, for instance, you can take an exponent of delta and think what this is equal to, or you can take 1 over 1 plus delta and think what this is equal to, and prove relations between them and so on. And this is a key to a lot of mathematics and combinatorics, and more than just combinatorics, it appears everywhere. Okay, so next time in lecture 4 we are going to do a few things related to trees, Catalan numbers, counting trees, and that's the last big generating function sort of story, and then we move to other things.